Hi everyone, myself Madhusudan. I'm studying in first year MSc Chemistry, JSS College of Arts, Commerce, Science, Hooty Road, Mysore. Today I'm going to present about thermodynamic probability and most probable distribution law. Before going to the topic, some introductions of statistical thermodynamics. This statistical thermodynamics is a mathematical framework that applies statistical method and probability theory. It is development of classical thermodynamics, a field for which it was successfully explaining macroscopic physical properties such as temperature, pressure, heat capacity in terms of microscopic parameters. This statistical thermodynamics has been applied in non-equilibrium studies and classical thermodynamics has been applied in equilibrium studies. So in this topic, thermodynamic probability, it is represented by omega. A thermodynamic system is taken and filled with an ideal gas of total number of molecules capital N, and they are distributed in K energy cell. Let N1 molecules enter first cell and N2 molecules enter second cell and up to so on Nk molecules enters K cell. That is N1 plus N2 plus N3 and up to so on Nk is equal to capital N. This equation we are using summation I is equal to 1 to K, Ni is equal to capital N. The number of A to distribute N1 molecules in first cell, Nc N1 is equal to N factorial divided by N1 factorial into N minus N1 factorial. Similarly, the number of A to distribute N2 molecules in second cell, N into N minus 1 C N2 is equal to N minus N1 factorial divided by N2 factorial into N minus N1 minus N2 factorial. Similarly, the number of A to distribute N3 molecules in third cell, N minus N1 minus N2 C N3 is equal to N minus N1 minus N2 factorial divided by N3 factorial into N minus N1 minus N2 minus N3 factorial. Now the number of A to distribute Nk molecules in K cell, that is N minus N1 minus N2 and up to so on Nk C Nk is equal to N into N1 minus N2 minus N3 minus and up to so on N into K minus 1 factorial divided by Nk factorial into N minus N1 minus N2 and up to so on Nk factorial. This denominator we are taking minus common, so this capital N minus capital N factorial is equal to 0 factorial. This 0 factorial is nothing but 1, so finally we are getting N minus N1 minus N2 and up to so on Nk. C Nk is equal to N minus N1 minus N2 and up to so on N into K minus 1 factorial divided by Nk factorial. Now the total chance of molecules distribute in all the cell, that is omega is equal to Nc N1 into N minus N1 C N2 into N minus N1 minus N2 C N3 and up to so on N minus N1 minus N2 and up to so on Nk C Nk. That equation we can simplify. Finally, omega is equal to N factorial divided by N1 factorial into N2 factorial into N3 factorial and up to so on Nk factorial. This omega is equal to capital N factorial divided by the product of I is equal to 1 to K into Ni. In general terms, omega N is equal to N factorial divided by small n factorial into capital N minus small n factorial. This equation we can using to calculate thermodynamic probability. So next one, most probable distribution law. As similar to first one, let us consider a thermodynamic systems having an ideal gas of total number of molecules capital N, which are being distributed in K cells such that N1 molecules enters cell 1, N2 molecules enters cell 2 and up to so on Nk molecules enter cell K. The thermodynamic probability of such type of distribution will be omega is equal to N factorial divided by N1 factorial into N2 factorial into N3 factorial and up to so on Nk factorial. That is equation number 1. The subject to the two constant, the first two constant terms is N1 plus N2 plus and up to so on Nk is equal to capital N. That is the first two constant terms. We can also written as summation I is equal to 1 to K, Ni is equal to capital N. That is equation number 2. N1 plus epsilon 1 plus N2 epsilon 2 plus N3 epsilon 3 and up to so on Nk epsilon K is equal to E, that is second constant terms. We can also written as summation Ni epsilon I is equal to E, that is second constant terms. That is equation number 3, where E is the energy of one molecules The mathematical probability of such type of distribution will be p is equal to c into n factorial divided by n1 factorial into n2 factorial and up to so on nk factorial. This equation taking log on both sides, log p is equal to log c plus log n factorial minus summation log n factorial. We can, in this equation we can apply Stirling approximation. Log c plus log n log n minus n minus summation ni log ni minus ni. This summation ni minus this capital N, so cancel to each other. So log c plus log n minus summation ni log ni, that is equation number 4. For most provable distribution we take minus delta into log p is equal to 0. This equation 4 we can differentiation with respect to delta ni. So minus 0 plus 0 into capital N into log n, that differentiation of constant terms is 0. So summation of 1 plus log ni into delta ni is equal to 0. That equation number 5. Differentiation equation 2, ni log ni is equal to capital N. This capital N, that is constant terms, that differentiation of constant terms is 0. Ni into this ni into log ni, that is product rule. We can apply the product rule. Ni into log ni, that is nothing but 1 by ni plus log ni into 1 into delta ni is equal to 0. Finally we are getting summation of I into delta ni is equal to 0. That is equation number 6. Differentiation equation number 3, that is summation I into ni into epsilon I is equal to 0. That is equation number 7. Using the Lagrangian conditions, we have summation I into 1 plus log ni plus alpha plus beta epsilon I into delta ni is equal to 0. That is equation number 8. This alpha and beta, these are the undetermined multiplier. So this summation of large terms is 0, which is possible only when the coefficient of all the delta ni must be 0. So finally we are getting 1 plus log ni plus alpha plus beta epsilon I is equal to 0. That log ni plus 1, that 1 can be ignored. That is ni is equal to e power minus alpha minus beta into epsilon I. E power minus beta is equal to a. Finally we are getting ni is equal to a by e power beta into epsilon I, where I is equal to 1 2 3 up to k. That is equation number 9. This equation we can use it, this expression give the most probable distribution in a thermodynamic system. Thank you.